Good morning, good night, good late evening, Bill.
Yes, it is quite late.
Yeah, yeah. We're sorry for that.
Yeah, hi Bill.
Philip,
Hello.
Yeah, um,
Yeah.
yeah. Thanks again. You managed to online. I'm quite worried about your time right now, 1 a.m. Right?
Yes.
Yeah, we wait for the Peter to join from Austria.
Yeah.
do I fancy that your beard has gone longer since the last we met?
Well, that's possible. I only cut it about once a month. It's one of the
Okay.
advantages of having a beard is I don't have to do anything to it very often. So when it gets toward the end of the month, and it's a little longer.
Is it, are there any issues of entanglement?
No, it seems to be pretty classical.
So thanks again, Bill, because this is one of the hardest series that I managed to set because you're in United States, Peter in Austria, and the host in Malaysia. And I tried to do it on when Peter at China, but I don't know. There's a problem in China. You want to use Zoom. So Peter
Okay,
told me
so good
about that.
morning.
Well, there's Peter.
Hi, good morning.
Good morning.
So hi,
Thanks for
Peter.
joining.
So, Bill, for you, it's very late in the night, or?
It
Yeah.
is indeed very late in the night, but now my calendar is telling me that you've just celebrated an anniversary.
Oh, that's right. Yeah, we've been married for 49 years now.
Wow.
49.
Oh, okay. Congrats. Happy
Well, that's
anniversary.
that's great. It's a perfect square.
Yeah,
Yeah, yeah. 7 square.
that's true. Yeah.
Perfect square.
So it's much more interesting than 50.
Oh, yeah, 50. Yeah. Did you celebrate? I mean, you have been married longer than 50, Bill, right?
Yes, we've been married 56 years.
56 years. Okay, that's long.
But of course, we got married when we were just children.
That's 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 exactly as old as I am.
Okay, so
Yeah, just give me a few minutes. We'll wait for a few more participants and then I'll go on to introduce both of you.
Okay. I think I'll get a little bit of caffeine to try to make myself a little more alert.
also my morning coffee here.
How's the weather at Austria? Fall? No, no, still summer.
Yeah, it's summer at the moment. Actually, we had a real heat wave, but during most of the heat wave, was visiting China, so didn't experience it. But in Vienna, I think for the first time in the recording, they had 41 degrees,
Oh,
which
this
is
time.
which is
Okay,
quite
all right.
hot. I mean, normally we
Yeah.
had rainy summers and whatever, but this time it's not really different.
Yeah, Peter, you mentioned to me that I just know that there's a problem using Zoom at China, right?
Yeah, that's right. And I mean, it's very unstable because then one has to use VPN to go outside. And I mean, these VPNs can be rather unstable. They work one day, but not the next. And I had actually problems using Zoom. There was at one point a press conference for the Metius Quantum Prize, and I was supposed to explain to the journalists, what the prize was about. And I was in a hotel in China, and everything worked well, but then it was cut off. And this is, yeah, this was a real problem. Yeah. So it's very unreliable. Yeah.
Oh, okay.
Well, of course, you can find unreliable internet almost anywhere.
True. Yeah.
I was in Lindau not long ago, and it wasn't At least at the hotel, it wasn't very good.
Yeah.
So
But they're going
Peter,
to shut the hotel down for a year and renovate it. So maybe there will be better internet as well.
so
Yeah,
Peter,
maybe things are
is
uncorrelated.
is it the first time that you get invitation from Malaysia?
First invitation from what? From
Malaysia?
Malaysia. Yes, the first time. Yeah, that's fine. So I feel very honored. Thank you. Yeah.
Yeah, have you been in Singapore before?
I was in Singapore, but never Malaysia. Yeah,
Okay, okay.
yeah, several times in Singapore.
So for Bill, this is a second invitation for this session. Yeah, thank you very much.
Yes, but always virtual.
Yeah.
So I tend to not think so much of the virtual visits as quite as memorable as being in person.
Yes, I would agree on that. Very much agree on that.
Um, Probably at 38 now. We start 39. Based on the pre-registration and the invitation, I think we have a lot of audience from Singapore. I know, Bill, you have a very good audience from Singapore. Yeah. So yeah, I think Prabha, we can start
Okay.
now.
All right. Okay, salam sejahtera, salam tengah hari, and a very good afternoon to all gathered here virtually. We are here for Cosmos of Curiosity, Series 32, a special dialogue series. Thank you to Dean of Faculty of Intelligent Computing, their respective officers, and broadcast control team here led by Mr. Sharizan for hosting this event. I'm Prabha, your moderator for this special dialogue series on quantum engineering, atomic precision, and quantum possibility. Our esteemed speakers for this special dialogue series, Prof. Phillips, formerly of NIST and University of Maryland, USA, as well as our Series 3, January 2022 speaker, which was then known as Isaacs, and Prof. Zoller from University of Innsbruck, Austria. Okay, good late evening, Bill, and good early morning, Peter.
Thank you.
Okay, I'll go on to introduce them. William D. Phillips received the 1997 Nobel Prize in Physics, shared with Stephen Chu and Claude Tanuji for developing laser-based methods to cool and trap atoms, technologies now widely used in modern atomic physics. He earned his Bachelor of Science in Juniata College in 1970 and PhD from Massachusetts Institute of Technology in 1976. Later joining NIST. There he pioneered laser cooling research, founded the Laser Cooling and Trapping Group, and co-founded the Joint Quantum Institute. His group developed key techniques in cold atom physics, including trapping neutral atoms, achieving temperatures near absolute zero, creating optical lattices, and manipulating Bose-Einstein condensates. Their work also led to atomic fountain clocks, now essential for global time standards. Peter Zoller received the Wolf Prize in Physics in 2013. He had graduated with a PhD in theoretical physics from University of Innsbruck in 1977 under supervisor Elotsky. In 1978, he received the Max Cade Fellowship to join the group of Peter Lambropoulos, University of Southern California. Returning to Innsbruck, he had held an assistant position at the Institute for Theoretical Physics and spent part of 1980 as postdoc in the group of Dunwalls in New Zealand. In 1981, he applied for the habilitation with a tenured position as docent. He spent the academic years 1981 and 88 as a JILA fellow at the University of Colorado, which is also a collaboration with NIST. And in 1986, he was a guest professor at the University of South Paris in Orsay, France. At the end of 1990, Zoller was appointed as a JILA Fellow and tenured full professor at the University of Colorado, and as co-director with C. Green of the National Science Foundation Institute for Atomic and Molecular Physics. In 1994, he was appointed as chair professor for theoretical quantum optics at the Institute for Theoretical Physics at the University of Innsbruck. Since 2003, Zoller also held the position of scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. In 2004, Zoller was a Loeb lecturer in Harvard and held the Yan Jiqi chair professorship at the University of Science and Technology in Hefei, China. In 2005, he was a Lawrence Professor in Leiden, and in 2008, Moore Distinguished Scholar at Caltech. Since 2014, he is external member of the Max Planck Society at the Max Planck Institute for Quantum Optics, Garching, where he spent a part of 2012 as Distinguished Fellow. Since 1995, Zoller has been Adjunct Fellow at JILA, University of Colorado. In October 2020, Zoller became Emeritus Chair Professor and at present holds the position of a Professor for Theoretical Physics at the University of Innsbruck. Peter Zoller is married with 3 children. We wish our distinguished panelists a very good evening and a very good morning. This is a unique opportunity to interact with 2 of the world's leading figures in quantum technology. If anyone wishes to ask anything, hope you can wait till the end of our dialogue, or it would be better if you could type it into the chat box and I'll take it from there. Thank you. Before we begin, please could Bill and Peter describe what are you working on currently in your respective capacities?
Okay, well, maybe I'll start, but one of the things that I wanted to ask of you probably before we start is, considering that our audience is rather diverse,
Yes.
If either of us give an answer that might be obscure to some of the audience, perhaps you could ask us to explain more.
Yeah, sure.
But sometimes we will tend to use jargon that may not be familiar to everyone.
Yes. Thanks.
So, okay. So, as you mentioned, in our research group at NIST, which is now part of the Joint Quantum Institute, we have succeeded in making extremely cold atomic gases, and based on work that was done, pioneered really in Boulder in the lab of Eric Cornell, we also make Bose condensates, which are gases of atoms that are, for many practical purposes, gases at absolute zero. And our work is mainly experimental work. We study various applications of ultra-cold gases. So, for example, one of the things that is an important part of our research program is quantum simulation. We can use these ultra-cold gases to, in a sense, realize in the laboratory idealized Hamiltonians that may or may not describe real physical systems. Because of the fact that the atoms are so cold, they can represent an idealization of things that might occur in, for example, in condensed matter systems. The atoms in our samples can behave in some respects like electrons in very cold materials, having the advantage that they're held in what we call optical lattices formed by the interference of laser beams that provide a kind of periodic potential for the atoms to move in, very similar to the way in which electrons move through the periodic potential of crystal. The difference is that our lattices are essentially perfect. They have no dislocations. They They don't have phonons. So many of the things that might represent complications in real systems are absent in the kinds of systems that we deal with. So this gives us the opportunity uh, to simulate behavior that can be, at least in principle, much simpler than what happens in real life. And in that way, we can study the kinds of things that happen in very simple situations. And the reason why this is important is sometimes those simple situations, as simple as they are computationally too complex to be um, to be computed on ordinary computers. And so we can do experiments where we can learn about what happens uh, in these idealized systems. I'm afraid that was a rather long answer, and I apologize for that.
No, that was just nice. Peter?
Yes, so I can say a few things what I'm interested in at the moment. So as you mentioned before, I'm a theoretical physicist, but I feel very close to experiments. I'm interested in experiments, and I'm interested in seeing the ideas that we have on the theory side in experiment, and also very often trying to build a bridge between theoretical concepts and ideas, and then trying to see them in the lab, as corresponding counterparts. And of course, quantum computing and quantum simulation is one of these topics. I guess we talk more about these things then also later. Also the quantum simulators that Bill just explained and also mentioned. But to sort of specifically mention two topics I'm interested in at the moment. So one topic, and this was done together with my experimental friends here at Innsbruck, Rainer Blatt with ion traps and the many ion trap groups that we have here, was the question. Today we are at the point of building quantum machines, quantum computers or simulators that we claim or want at the end to be more powerful than their classical counterparts. How are we sure that the predictions or the results that these machines give us are actually true when we cannot test them classically? So that's a question of verification, and we had some ideas along these lines, and we just wrote a very long paper that will be published in Physical Review X now very, very soon. But we had kind of a theory/experimental approach to these things. And to mention a second topic that also illustrates the kind of interest that I have right now, people are building quantum networks, for quantum communication. It's, I think, one of the most fundamental applications that we have here in quantum technologies. And we usually think about quantum communication networks for secret communication. But you can also reinterpret some of these possibilities or experimental abilities as building a quantum sensing network where you would like to do quantum metrology, and maybe effects like from gravity, are accessible by using the tools that we develop for quantum communication, but now in a quantum sensing context. And we have a paper submitted together with my friends at, for example, Chilla, and also local people here that discusses these kind of options. So these are two illustrative examples from ongoing work.
If I could just make one more comment. Peter said something very important, which I want to emphasize to especially the young people, that he is a theorist who likes to be very closely connected to experimentalists. This is just the sort of theorist that we experimentalists love. And so for young people who may be beginning careers as theorists, being closely connected to experimentalists is something that we greatly appreciate.
Well, I can only add from my side, it's great to work together with experimentalists that are so powerful, that ideas that seem like a dream at the end make it to the lab. And I mean, that's the fruitful connection, I would say.
Hybrid rare species. Okay, and with that, we kick off with an open question to both our panelists. This question is an interplay on theory and experiment. So quantum engineering thrives on the interplay between theory and experiment. One has been used to prove or validate the other. And now it's moving towards using the hardware part of this interplay for real world applications, i.e., quantum computing and all this stuff. Is this sustainable? And what are the most critical challenges and opportunities in ensuring that theoretical breakthroughs translate effectively into real-world quantum technologies?
So
Well, one
Billy
of the
wants.
things I'd like to point out is that Peter uh, is one of the principal pioneers in this area. That is, he was the one who proposed the way in which the first quantum gates should be done, and this was actually realized then in Dave Wineland's group. So the the interplay of theory and experiment uh, really produced the very beginnings of quantum computing, and it was because of the theoretical ideas that Peter and Ignacio Serac had that led to the first quantum gates, which have, and that was now 30 years ago, right?
Yeah.
And uh, and now we've advanced so much further than that. Now I'm not quite sure what the question meant about is it sustainable? Could you just say a little bit more about what you meant by that? You're
Sorry,
muted.
sorry. What I meant was we usually balance theory feeds, theory predicts, and then experimental proofs or experimental disproves, and they feed onto each other. And then now we find that this whole hardware part is moving on into the real application world. So where does theory come in? Where does hardware come in? Where does experimental come in? Can this be sustainable for the application side of it?
Well, I don't see any stopping of the kind of fruitful interplay that you talk about. We're still, as we make hardware advances, we're still very much in need of guidance from the theory side. But maybe Peter can say a little bit more about that.
Yeah, I would say that, when I go back to the early stages of my own career, theory and experiment have at that point always been quite separate in the sense that maybe there was a theoretical idea, but it took quite a long time for experimentalists to pick it up and then verify it, or experimentalists came with ideas, results, and so on, and theory had to work on that. So this kind of a feedback loop was rather slow, I would say. But this has changed fundamentally since we started working on, for example, quantum computers and people build in the lab universally programmable machines. I can literally say, as a theorist, you might have an idea in the morning, and in the afternoon you can try it out together with your experimental friend. So it's really amazing. And also this feedback loop of idea, trying it out, and then getting new ideas based on the fact that you tried it out has become much, much shorter. And I would say that this is sort of the defining element of the present period that we're in. And this sort of very fast cycle has changed life, I would say, quite fundamentally in our collaboration, but also in terms of, how this cycle of feedback loop, new ideas, and so on is actually progressing. Yeah? And along the lines, I should then also say that, when you talk about challenges, I would say that in this context, these challenges are that, first of all, we are trying to build, of course, larger and larger machines, in light of error correction. But the other challenge is that we are in a time of, you know, we speak about applications of quantum computing. We have the most powerful machines we came. But I would say that the problem of finding applications that are also maybe relevant, outside of physics for industry and so on, I would say that this is quite a big challenge at the moment. We are well on the way of building a fault-tolerant quantum computer. But if you ask me, what the real applications are that might be industry applications and so on, then the answers are not so obvious. We have a very few that are real killer applications, but finding compelling applications, I'm sure that this will come. But if you ask me for challenges, this is one of them. And of course, the last point in mentioning challenges is also what I said before that I'm interested in is this: we build these powerful machines. How do we verify and certify them that they cannot cheat us, when we have no way of classically confirming that the result is correct and checking them?
I
If I could just
suppose.
add one more point to this, one of the things that I find particularly satisfying and exciting is that uh, theoretically, there have been developed some quantum algorithms to do things like, for example, scheduling of routing of for example, delivery systems that initially appeared to have a quantum advantage over the way in which one could do these things classically. But once seeing the quantum algorithms, clever programmers were able to produce classical um, uh, programs that could do as well as the quantum programs. So these quantum-inspired algorithms have really been marvelous in improving certain things. But at the same time, what it meant was that the quantum machines weren't the ones that were really doing the job, but they inspired new things from the classical programs. I think that's just wonderful.
That's cool. That's cool. Just working on algorithms.
Yeah, and this should maybe add also one point over here when we talk about algorithms. Of course, many of these algorithm ideas are developed in a quantum computing setting at the interface between physics, mathematics, and also computer science. But it is very interesting from a physics point of view to then take some of these ideas there and bring it back to physics. For example, in the case of quantum metrology, you might do a database search, in computer science, which is a very important and interesting problem, but bring it back to physics. How can we study in quantum metrology the searching for lines that you are trying to discover, like the thorium clock line, how do we do spectroscopy? So are these new ideas and tools also useful in physics per se? And I think just this interface, quantum computing, quantum metrology, and so on is also, along the lines of, I think, opening completely new doors in the way that we did not expect before.
Thank you. On the next question, moving to a bit of AI. Now we know that AI has been used to predict or plan out or even simulate a certain stuff. So the question is, how do we envision the relationship between quantum technologies and AI evolving together? Will there be a positive feedback that will power each other, meaning that AI be able to predict or improve quantum algorithms or quantum findings, or will it be there will be a break somewhere?
So should I maybe start here, Bill?
Yeah, sure.
Please.
So I would say that AI at the moment is already transforming quantum technology as a significant impact, but whether quantum technology will also transform AI, and this is, I guess, what you were really asking, is still quite an open question. And I would say that from my perspective, there are actually three questions that one can ask and try to answer here. So what can AI do for quantum technologies? And the second question would be, what can quantum computers do for AI? Do they lead to a more powerful classical AI by running them on quantum machines? And maybe the most interesting one would be the third one, if all of this can trigger some genuinely new forms of quantum AI, where quantum gives possibility that classical AI from a conceptual point of view does not provide. So I guess that the answer to the first question, what can AI do for quantum technology? I would say that this is at the moment has very real impact. And because AI, in a very broad sense, is a very powerful engineering tool. And today we're using machine learning to calibrate and control quantum devices. Well, I mentioned before the verification ideas, and we're using Hamiltonian Liouvillean learning, which is a form of quantum computing simulation together with machine learning to learn that machines do whatever they are supposed to do. So this is becoming a tool, okay? And another example along these lines would be, at the moment, we are in the era of quantum error correction. I guess we talk more about this and also later on, where AI helps us to analyze quantum machines, find what are the dominant errors and so on, and then really tries to find, for example, a quantum error correction code which is matched to the abilities of the machine and to the mistakes that the machine makes. And so this is a powerful engineering tool. When it comes to, what can quantum computers do for AI, I would say this is not so obvious. Of course, we have certain quantum algorithms like solving linear equations, this HHL algorithm that are very powerful, more than classical in solving linear equations. These are useful things in AI, but if they're really a game changer there is something that I doubt. There's fundamental problems there. How do I load a lot of classical data that I need into quantum memory? This is again a problem which is not entirely obvious, but my colleague Hannes Pichler here has actually worked on some of these ideas, and there may be answers coming. But the third point is there genuinely new form of quantum AI, where quantum sort of with entanglement and superposition provides a new form of doing AI. And this is most speculative, but I will also say most interesting. So we would have here really sort of new computational paradigms where you have, for example, you want to do a mathematical proof, and you develop, your data, quantum data, superposition and huge entangled states in your quantum machines. And then you're doing, for example, searches, to make proofs, automated proofs that work on the basis that you got quantum memory there. These things are stored in the superposition state. And then, for example, using robot database search to find, a particular answer that you would like to have. I think that all of these things have not been developed at all. But this interface of really using quantum in superposition and so on, together with AI, I will see that there's some potential, but I think at the moment it's not really much more than just some simple ideas.
Oh, that's complicated. What do you mean by quantum in superposition?
Well, what I mean is this, that, classical data, when we load them, into a quantum machine would be just, this or that, and so on. But you might have a situation, for example, when you're doing a mathematical proof that you have the coexistence of quantum data, So quantum data as a quantum register, which can be in superposition. This provides a new data, okay? And this new data then allows also the powerful quantum algorithm to be applied to that. And if you can formulate the problem this way, then this may be an interesting way where AI and quantum meet at a novel level, where quantum really provides something unique to the story and is not only just acceleration.
Okay, so it seems that at this point, it's a beginning of a positive feedback between quantum and AI.
I would say so, but yeah, we'll see what the outcome is. Yeah.
Okay, yeah. Bill, anything from you?
Well, if I might just add a philosophical perspective to this, one of the things that is sometimes troublesome about AI, or at least some of the implementations of AI, is that you get a result, but you don't necessarily understand how the AI came to that result. And of course, part of the problem with that is you aren't sure whether it's correct. AI is well known to have hallucinations.
Yes.
But there's various ways of checking that. But the philosophical question that arises is, if the AI produces results and you can verify that the results are good, that it correctly predicts, for example, how a physical system, a complicated physical system, will behave, what's the nature of your understanding of that physical system? In contrast to the sort of old-fashioned theoretical way of doing things, where you may derive an expression that predicts how a system will behave, and it's an analytic solution. When it's done with AI, and the AI can't even explain to you how it came to its conclusions, have you understood the physical system? Or how should you think about the difference in understanding in that way as understanding in the more classic way? As we think we've understood electrodynamics because we have Maxwell's equations. Will there be that kind of understanding when AI is telling us how many body systems that are highly entangled are going to behave? Will we have the same kind of understanding? It's in some sense a a philosophical question, one that is interesting to think about, and it may depend to some extent on how the AI is configured. That is, you may be able to configure an AI in such a way that you insist that it be able to tell you how it came to its conclusions. And I've been told by people who write AI programs that you can do them either way, and it's actually more powerful if you don't ask it to explain itself.
Don't ask, just explain. Okay.
Yeah. But maybe I can add something to that very short. So I would say that the question that Bill points out here is a very fundamental one, but it was even earlier in physics when you're doing, for example, theoretical physics as a numerical person. You know, you're solving a complicated problem on a computer, you get some results and you get a beautiful curve. Maybe it agrees with the experiment. But numerics never explains to you what it does. You know, it may obviously be right, okay, but it doesn't explain to you. But then I would say it is the art of asking questions, you know, in your model. I'm leaving out this, I'm leaving out that, you know, what was the essential part? So there's then this interactive, you know, discussion going on with your numerics or with your AI or whatever, that at the end, you know, gives you the physical picture and points out the important parts. So I would say what AI really provides now is this interactive interface, you know, of us asking questions, getting answers. Based on the answers that we get, we ask some other questions that will lead to understanding. So AI not only should give answers, but also teach us, you know, why these answers are the ones that we get and why this is important versus that.
Yes, I agree. I think that's a very good point that once we had uh, numerical calculations, especially with very fast computers, so that we could change parameters and in almost real time see what the differences were. We were already facing this kind of question about the nature of understanding, and AI, I think, is just another step along that road.
That was nice. Good. Peter, I want to ask you this. Aren't you afraid that quantum AI might replace you? Not Bill yet, because Terminator is
Well,
not
the
there
honest
yet.
answer is I'm too old, you know.
I don't care.
Uh, no, but I think that there will always be, you know, AI provides a very interesting new tool that we as physicists or as societies have learned how to use properly. And new tools give new opportunities. They also new danger and so on. And it's just up to us to, you know, apply the new tools in a constructive way. So I think we're not afraid. We have to identify opportunities.
Okay.
I'm reminded that hundreds of years ago, when printing presses were first invented and it became possible to widely distribute books,
Cool.
that people said, "Well, this is the end of teaching by human professors.
Okay.
Uh, there's no need for human professors because you simply have a book." Well, obviously, that didn't turn out to be true.
Yeah. It became more.
And I don't think that it will be true that AI will eliminate the need for humans. I mean, it's very difficult to say, well, AI can never be as creative as human beings, and I think that's true right now that AI is not creative in the way that humans are. To say that it will never be, well, it never is a very long time,
Yeah,
so
never.
it's hard to know.
Yeah.
But I don't think that we're going to uh, get rid of the need for and the importance of humans because of AI any more than books replaced humans.
Yeah, but I'll still leave it out there yet. We have not seen like what Peter said on the creativity side. We have not seen something like that coming from AI. But if and when that day comes, that's the thing. Okay, I'll go on direct to a question to Peter on
Yeah, I think I want to add because I'm agree with what Peter say about AI, and it's not like you Google something in the internet that the AI now you can interact. If you interact with the AI, so this kind of thing will give you some sort of discussion for you to decide whatever you do in theory or experiment. So I think it's again back to the human to decide, not AI to decide whatever you want based on your knowledge, how curious you want to find the information. That's it.
Yeah, I would agree with that. Yeah.
That brings me to a rather dangerous point. Bill and Peter, both of you are old guys who are very steadfast in your in your theory and your experiment. What about young guys who are starting out? Can they be misled by by this AI, especially on a strict term doing quantum technologies? What do you think, Peter?
Well, clearly, the young generation is the future, and they see at the moment what we do, for example, in quantum technologies, and for them, these are new opportunities, and they have to approach it, with the tools that we have right now. And I would say it's, for every generation, they see, what's at the table, what the tools are to work on these things and making use of that. And I will say that the young generation will know how to use it in the most productive way. And when I think back to myself, that I was educated as a theoretical physicist, just writing a few equations and only analytical formulas, and numerics was very hard. And there were the early pocket calculators that we got very excited about, that we had an HP calculator with 120 program steps. Okay. And now we have huge computations. They learned how to use these things in a very new way as a tool to do new physics and answer interesting physics questions. I would say that it's the same now here, that we have new tools available that will be amazing if you learn how to use them right. And young generations are the one that always, lead this forefront. And so the future is with the young people, based on their ability to be much more open to these sort of new tools that are coming and learning how to use them properly.
At the same time, it's hard for me to see that AI is ever going to be able to decide what are the good questions. Now, maybe that's just because my imagination isn't fertile enough to imagine how AI will do that. But it's hard to see AI having the same kind of curiosity that people have. But another, I think, important job of the young people who are growing up with AI is to make sure that AI doesn't make mistakes. I think we can see that with each generation of AI that comes out, there's less in the way of hallucinations, less in the way of obvious mistakes. But it's going to be harder and harder to detect these mistakes as we go on, and that's going to be a real challenge for young people.
And maybe I can add one additional element to the whole thing. Sort of traditionally, when we work in physics, there's maybe senior PI, postdoc students, and so on. I would say that there's another, under quote, person now sitting at the table, which is AI. AI is, well, if I have a completely new idea and I want to do the postdoc on Saturday night, maybe this person has other plans and so on, and not be open to hear my newest thought, what I would like to discuss. AI is, of course, there. AI is never tired, is always friendly, and so on. So I find that there's sort of a new person at the table, which is a little bit different, and we have to sometimes see if this person is really makes sense or not. But I think it adds another discussion partner that we just have to use properly, that we cannot always trust, but we can ask a lot of questions, And I say, I got this great new idea, and then AI answers, well, sorry, you're a little bit too late because 10 years ago there was this paper that actually discussed what you talk about. I find this very helpful, but it's one additional, under quote, person sitting at a table who is always friendly, never gets tired, but makes mistakes. It is sometimes also pretty stupid. Yeah.
Nice, nice. Okay. Peter, a question for you. On quantum simulation and stuff. You have been a pioneer in quantum simulation. How much of quantum simulation is currently using AI, and which class of problems, materials, chemistry, or fundamental physics, do you believe quantum simulators will solve first, in a way that classical systems cannot?
Yeah. Okay. So these are two questions, and let me try to answer.
Yeah.
So let me say that I would say that the topic of quantum simulation, and by quantum simulation we mean here that the quantum machines like quantum computers or sort of specialized quantum computers that we call quantum simulators will, under quote, solve a many-body problem, a Schrödinger equation, which is very hard to solve by classical techniques because we got huge entanglement and so on. I would say that this is one of the applications in the context of quantum that we are very sure about that will have fundamental impact. The answer is very clear. Quantum likes to solve quantum problems, and so quantum machines are in this sense more powerful than classical machines will ever be. When we talk about the interface with AI, sort of here, and the other question was more about, what kind of application or usefulness cases we have here. AI, I mean, I mentioned before verification. And for example, we've been using machine learning to ask, okay, well, my friend, experimentalist, built a beautiful quantum simulator. Does this thing really realize the Hamiltonian that my experimental friend and I think is there? Are there additional terms there that we're not in control? So at that point, you can use machine learning, to find out, what is the real Hamiltonian, the real Liouvillean in the sense of a master equation, to describe this thing, to model that. And this is a very important tool that allows us to characterize quantum machines in the regime of quantum advantage, where we cannot do that classically anymore to check this. And so this AI machine learning kind of things provides the answers that are part of the toolbox, how we approach the problem in verification. And the other question that you were asking has to do with, application cases, where are these things useful? Will they change our life? We always promise, we build quantum computers that will have an enormous impact. Where is this impact? And I would say that one way to think about this interface with AI is what I call this, under quote, inverse quantum simulation. What we're doing at the moment, quantum simulation, is that we always say that, well, here's maybe inspired by some real quantum material and interesting Hamiltonian. I would like to know what the phase diagram is, So, and then we take this Hamiltonian, we have a digital or analog simulator, put this thing on our quantum machine, and we get the answer as a phase diagram, that explains if this Hamiltonian is written down, the answer is this phase diagram, and this is what the quantum simulator can do in a sort of programmable way. But I would say that you can also go the other way around. Like you can ask, what about me drawing the phase diagram of my wish material? I have a wish list of properties from a material. And if a chemist could actually synthesize this material, it would change our life because it has certain properties like, high disease, superconductivity, or whatever these things are. But then you can ask the thing, can I go backwards that I write now the wish list, and I use a quantum machine in order to tell me what the Hamiltonian is that would actually generate these results. So it's just the opposite of quantum simulation, not going from microscopic model, quantum machine, and then the answer. But there you actively say, this is what I want, and what kind of things, I have to write down. And of course, this has been done classically. People are doing that, but quantum machines, I think, give you new opportunities. And it is this, instead of going from Hamiltonian quantum machine, discovering some interesting phase diagram, it is much more like, actively asking for active design. I write down this phase diagram, I draw it by hand. What does it need on the Hamiltonian side to lead to these features? And I think that we're in the phase at the moment that this is really, here's quantum machines that enable us to solve these things, but AI is kind of steering this by providing cost function, optimizing them on the quantum machine that will answer this question. That for me is sort of an example that I find at the moment very exciting and goes beyond the standard paradigm of quantum simulation we have thought about so far.
Oh, that's nice. Is it as fast as classical systems or faster?
Well, you want to use, of course, to solve, for example, when I write down a wish list of materials, I say that, I want a high DC superconductivity. And you can formulate these things as a cost function. I said that, I want this property, this, and you write down the cost function. And this cost function could be, optimized classically, but since the underlying physics is a many-body problem that classical machines have difficulty solving, quantum machines from the very beginning have a very good starting point, and you can try to play these games. And we have been doing that recently, and Yeah, so I would say quantum machines provide really the ability to solve this optimization problem in a much more powerful way, and therefore provide us with answers that hopefully lead to new discoveries in this sense of being also then useful for the world out there. You know, when we say that quantum machines allow us to do something that also society will benefit from.
Okay, thank you. Over to you, Bill.
Well, so there's a question that I'd
Yeah.
like to pose to
Yeah.
Peter about this. Peter very correctly and clearly stated that one of the reasons why quantum simulation is so powerful is because we have these many body systems that are highly entangled, and ordinary classical computers can't handle them. In the 20th century, we learned a tremendous number of things by making an approximation, sort of a mean field approximation that turns a many body problem into a few body problem or a single body problem. And now we're saying, okay, that was great, but it doesn't get at everything. There are many body issues that aren't going to be able to be addressed by that kind of a mean field approach. What I'm wondering is, how confident are you that by doing the real many body problem, we're going to see something new?
Well, I would say that, you know, if I take as a starting point, what you said before is that, you know, you got a many body problem and you can do an approximation, and there's mean field theory that gives us answers. And very often, I mean, if you go back in condensed matter physics, fantastic answers that really gave understanding. But there was then also, of course, you know, strongly correlated materials where we know that mean field fails. And I would say, no, in theoretical physics, there's always the question, you know, I have a Hamiltonian, and then person A, B, C has very great ideas, and very often, you know, by writing down a certain variational wave function, wins a Nobel Prize for that. Think of Loveland and so on. I mean, we have many examples, you know, they're just very clever, and it's obviously the answer. But you know, if I look at it more from a numerical point of view, here's a Hamiltonian. I really would like to know the answer. Can I give an answer which is certified? And mean field theory does not do that. So it gives you a very good clue, but you know, very often does it apply? Not. I mean, there's this ambiguity. And to be honest, if I'm an engineer, you know, I have here my equations and I would like to get the answer, and I want the answer with a controlled error. Okay, and this is what say has been a lot of progress on the condensed matter side and theory side with techniques like density matrix renormalization group that provide, you know, for very special situations, quantified errors, saying that, you know, I can guarantee that the answer will be correct, you know, up to this error bar that you can assign, and there's a systematic way of improving, so you can trust the answer. Okay. And so in that sense, I would say both quantum computing is able to solve problems, you know, provided that we can certify or verify it, you know, that are trusted answers, that we really know that they're right. Mean field theory can be completely wrong. And by being clever, you can win a Nobel Prize by writing the right, you know, variational wave function for this and that, be it BCS or be it fractional quantum Hall effect. But I would say that from practice, we want answers with an error bar. And, you know, this is what the challenge is. And mean field theory definitely does not provide that, you know, even though the clue that you get is very often fundamental.
Bill, you happy with that?
Well, only partly. I mean, it's no question the mean field fails, but I guess the real question is, will solving the many body problem correctly give us something that is new and surprising? Well, you know, we don't know what the phases of, as you pointed out, there's many body problems where we don't even know what the phases are at zero temperature. And but of course, we haven't learned those yet either in these quantum simulators. I think we're on the verge of learning about these things.
Yeah, but Bill, I have to say that, of course, in what you add now to the discussion is sort of a new axis. Before we talked about, you know, here's a problem, let's solve it, and let's be sure that it is right. And quantum machines provide a very good way of doing it, even in the regime where mean field, for example, breaks. What you are now asking is the result interesting, you know?
Yeah.
It's a different axis, of course, the axis that we are really interested in, you know?
Yeah.
And that's a very subjective. Maybe this is what AI is not able to do. Finally, we find an example. And this is really what physicists are doing. And because we want to find interesting, exciting, surprising answers. And but you know, if I get an answer for a problem and it is surprising, I also want to make sure that it's right. So I would say that our discussion before about understanding and
Yeah.
really being sure that our answers are correct are sort of, you know, the starting point for this. Okay, well, here's really something new, which is not an artifact of mean field theory, but is interesting. But the interesting component is always the discovery at the end. And so you know, it becomes very subjective, you know. But I know that you and I get excited at this point, you know.
Nice to see you guys excited. Okay. Bill, a question for you. Your pioneering work in laser cooling has enabled extraordinary control over atoms. What do you see as the next major practical breakthrough that could emerge from ultra cold atom technologies? As with everything else, except planes, ships, and homes to an extent, can we shrink these technologies, maybe to a lunchbox size for starters, and ultimately to VLSI chip scales?
Well, certainly things will be able to be made smaller. Today, many uh, quantum computing platforms take a room full of equipment. And there's no question that if it becomes important to reduce the size of these things, that will happen. But I think that it's hard for me to see a quantum computer having as many quantum bits per uh, square centimeter as you have classical bits per square centimeter in a classical computer. So one of the reasons is if I look at at a a platform like neutral atoms or ions, if I want to individually address these atoms, at least using the kinds of techniques that we use today. And I'm not saying there can't be new techniques, but if we stick with the kind of techniques that we're familiar with, these things can't be closer than about a wavelength of light. Whereas we routinely put uh, classical bits, basically transistors, written at a tiny fraction of the wavelength of visible light, at least. Part of this is because lithography has been pushed not just to shorter wavelengths, but also using all kinds of tricks that allow you to have better resolution. Now, some of those tricks, maybe not the same ones, but there can be tricks that allow better resolution in addressing, say, neutral atoms or ion qubits, as you can use the same kind of techniques that are used in tomography, for example, by putting gradient fields on and using those gradients to address just the bit you want, even though there's another bit within a wavelength of light and you're shining light on it, you can make it invisible because of the fact that you have a high gradient field. So there's all kinds of things that might make my initial estimation that it's going to be hard to make quantum computers as dense in their qubits as classical computers. But at the same time, we typically don't need as many quantum bits in order to do interesting things as we need classical bits to do interesting things with classical computers. So the answer to your question is, I don't know. A lot will depend upon how things work out, but things are definitely going to get smaller. I think that today we are at a stage in making quantum computers that might be analogous to where we were in the 1950s with classical computers, when we had a whole room full of equipment that was not as powerful as powerful as a watch is today. So there's a long way to go in improving the physical platform on which these quantum computers can be realized.
It's not that they cannot be done from your original atomic clock to what is flying around in space right now, which have been shrunken down, so it can be
Well,
done.
and it's even better than that. People are
Yeah.
now making chip-size atomic clocks.
Yes. Yes.
So we may find an atomic clock in your cell phone
Wow.
in in the future, and some of those atomic clocks might be nuclear clocks. Because of the fact that Peter brought up the idea of thorium. This is this wonderful transition in the thorium nucleus that is within reach of lasers. And the beauty of this is because it's a nuclear transition, it's much less affected by outside influences. And you can imagine putting the thorium nuclei in solid materials and operating at room temperatures and being able to do things, well, not as good as the very best atomic clocks of today, but awfully good. Good enough that it will make a big difference in the performance of things like navigation programs that you have in your cell phone.
Since you brought in semiconductor, there is a question by Dr. Sharifa on the chat box. The semiconductor revolution was enabled by our ability to control electrons with ever increasing precision and scale. As we enter the era of quantum engineering, what lessons from the semiconductor industry could be applied to quantum technologies? What fundamentally new challenges make the quantum roadmap different?
Well, I think one of the lessons is that it's difficult to imagine how wonderful things are going to be in the future. I remember a time in the 1980s when the leaders of computer companies said there's no reason why anyone would ever need to have a computer in their home. Today, of course, we have hundreds of computers in our home, and we hardly realize that there are computer processors in so many of the things that we have in our home. So the inability to imagine how wonderful things are in the future is, I think, one of the lessons that we should take from the past. Peter?
Yeah, I would say that, at the moment we are actually in the phase in the quantum computing context where, we are less thinking about how do we get it smaller and all of these things. These are very important questions, but in the long run, I think at the moment in the phase that we would like to demonstrate that the concept, for example, of a fault-tolerant quantum computer works. And having platforms like, from superconducting all the way to atoms, ions, and so on, provides us with platforms where we can develop these things. And all of us know these are not the final answers, But to demonstrate fundamental concept, like, for example, quantum error correction that you can implement in the lab, that you can take these systems, that you can scale them up, they are relatively slow at the moment. All of these kind of complaints that we had. But we can nonetheless put them together in a package, that at the end, I think on a scale of a few years, will provide us with experimental fault-tolerant quantum computers where we can see that this fundamental concept of quantum error corrections, errors not spreading during computation, that these things work in the lab. And I would say that it is only after that, that will start asking questions. Well, my complaint is neutral atom arrays. They do all of these things very beautifully. They scale up and so on, but they're very slow. Okay, so maybe at the end, the answers will be more on the solid state side, going smaller and smaller. But I see this in more as an engineering, technical kind of developments. And I would say that right now we are in this very interesting phase where we have, 30 years ago had ideas, then first experiments of building blocks. Now we scale them up and now we demonstrate quantum error correction, fault-tolerant quantum computing, and we're able to do it in particular systems. And this sort of cleaning up and making it better and then also more useful is sort of a more engineering type stage that will come later. So I appreciate all of these things, but I would really also say here, I'm intrigued by the progress which is just made right now. I remember a few years ago, I was part of a writing team for the National Academy, for the 10 coming years in atomic physics, what will happen. There was this section there that said quantum error correction. And I told to the other ones, is it not too early to talk about it? No, it was not too early, and now we have reality. These things are happening right now in the lab. And it is sort of, seeing in the lab happening what our dream was, what we promised, and that these fundamental concepts work. And then sort of improving them once you get them to work is kind of a separate stage for me. Will be the next generation that we talked about before that, might take up these things, and it's much more an engineering task. And at that point, of course, solid state physics is coming back in again in a very new way. But let's first of all show that we can really scale up systems, that we can control decoherence, that we can have high fidelity gates, and all of this we're able to do right now. And clearly, they are not the final answers, but they demonstrate the concept.
That brings to my mind, if you say that we can have a fault-tolerant quantum system, by fault here I also include energy requirement, thermal requirement, and all that. Are we over investing on on the current AI hype on energy requirement and power requirement and all that stuff? What are these guys going to do? Are they going to dismantle everything?
Yeah, I mean, now we are sort of back at this interface between, quantum computing and then AI and so on, and we discussed it briefly before. So I would say that, I mean, in this interface with AI, my answer is really there's a completely new AI on the horizon by sort of really doing it quantum and having superposition states of different data and work on them, But the basis of all of this is that we need the corresponding hardware. And the fantastic thing right now is that we are now, just at the verge of being able to build this kind of a hardware, maybe in the most primitive form, but in the first time when we can try it out. I mean, think of classical AI. A lot of these ideas, were very old, maybe 50 years old, and it was the development of hardware that allowed one to try these things out. And many of these algorithms that we have in AI are purely heuristic. And but we can try them out on hardware. So I would say that this element of having a machine and you can try out your ideas that are maybe theoretically not clean at all in a heuristic way, and then you see, wow, this thing works. Maybe it works even much better, like large language models. And of course, there have been a lot of new inventions, but this sort of cycle, better hardware, ability to do something there, leading also to new ideas, being able to try them out, see they work, pointing out in what direction, and sort of there's this feedback loop. And this is exactly the feedback loop that I also see at the moment going on in this quantum context, that we, for the first time, built the hardware that will be the enabling step for this rapid co-design feedback loop, an idea, trying it out, and then Mel getting new ideas and so on.
In that sense, for your next question, how can theoretical frameworks better guide engineers in building practical quantum devices, given the gap between ideal models and noisy real-world systems?
Well, I would say that first of all, let me say when we talk about noise and so on in the quantum system. So I wrote together with Crispin Garner a book about quantum noise, and I'm always like to quote here Jan Hall at Chile, Nobel laureate, and of course known for building the most stable lasers that we have in the world today, frequency comms and all of these kind of things. And he once made the statement, and I really love it. He said, "Make noise your friend." Okay, so I think that we have to rephrase that now by saying that let's make quantum noise our friend, when we talk about all of this engineering here. And quantum noise, our friend, means that noise will always be fundamentally part of the whole story, while we are trying to isolate systems better and better, getting better and better qubits with high and high fidelities and so on. Of course, we have these, some contradictory requirements of isolating systems. But if you want to make a measurement, you have to couple to an environment and then make the measurement there. So this concept of making noise your friend, being part as something to be maybe even used, in how we design these machines. I think that this is the right attitude. So let's not fight it. Let's make our friend, and let's find where with our friend we can find common ground where we can progress. And so, yeah, so Jan Hall, in this sense, translated to today, let's make quantum noise our friend. I think that's the right message and also the guiding line for engineering.
Cool. Quantum noise. Make noise, our friend. All right. On Bill, on the experimentalist standpoint, what are the biggest technical barriers for scalable quantum technologies? Noise again?
Well, that's a question that doesn't have a very simple answer. Uh, there's a number of layers that by which one might answer that question. So on the one hand, sort of the high level view is just what Peter said, that you have this tension between wanting to isolate your qubits from the environment and being forced to connect the qubits to the environment in order to be able to manipulate them. So decoherence is the enemy of quantum computing, and decoherence comes about, at least in part, by connecting to the environment. Well, that's not really the only way in which decoherence comes about. The fidelity of gates the infidelity of gates produces a kind of decoherence as well. That is, if you operate a gate, let's say you operate on a qubit that is in an eigenstate of the qubit basis and put it into a superposition state, and you're uncertain as to what you did, that is a form of decoherence. The fact that you don't know exactly what kind of a superposition state you created is a kind of decoherence, in the same way that having that qubit being connected to the environment, the fact that there might be stray fields around that could also influence the qubit, or in the case of superconducting qubits, the fact that the qubit is connected to a refrigerator. This is an environment that provides a low temperature but not zero, and the fact that it's connected to a material that has embedded in it mysterious things that go by the name of two-level systems, that we don't really know what they are, but we know that they do bad things to our qubits. So there's this tension that exists that Peter described. So that's one thing. And another thing is, again, something that Peter described, having fault tolerance, having the ability to do error correction well enough and repeatedly, so that the decoherence that is a fundamental part of any physical system does not destroy your ability to do a long computation. That, to me, one of the big milestones that I want to see is the creation of an immortal qubit, where, in spite of the fact that this qubit is subject to any number of decoherence processes, that I can keep it with, I can keep it alive, so to speak, that I can keep it so that it has enough coherence to do the kinds of calculations that I need to do for as long as I need to do those calculations. In the end, that's got to happen before we have the kinds of quantum computers that we want to do really important long calculations. So that's another way of saying, what is the challenge? But then at the level of the details that are going to be operating for any given quantum platform, there's the question of how do we solve the problem of the so-called two-level systems, these sort of mysterious features that cause decoherence in superconducting qubits? How are we going to solve the problem of imperfections in the gates? The fact that it's very difficult to stabilize the power of the lasers that are being used to manipulate these qubits at the level needed to produce the kind of fault tolerance that we want. I don't believe that any of these things are impossible, but they're all hard. And the further you go toward what you want, the harder it is to go to the next step. And I've been absolutely astounded at how much progress has been made. That is, it always seems that these hard steps, people figure out ways of doing it, and it's just been wonderful. We need to continue to have those astounding advances in order to get where we need to go.
Can I add something over here, which I think is sort of very important? That I would say that all of us, I mean, what just Bill said right now, that there's no fundamental limit, and nature seems to allow us to build machines like a quantum computer, which at the end, using error correction or whatever, topological qubits and so on, will be perfect, and there will be the immortal qubit that does infinite long calculations and so on. Seems possible, okay. But at the same time, I have to say that I'm getting a little bit afraid. So at the moment, we are in the middle of this race. It's always make this analogy with climbing Mount Everest. There's teams of group that want to climb. There's this other group over there. They're a little bit faster. Let's try to catch up. And then you reach finally the top, maybe together, maybe one before the other one. And then you ask yourself, why the hell did I climb it? What was the motivation? So I think that we have motivation to build these quantum machines, and I would say that many of the real things need to be discovered. But I would like to say that it is very important, while we are doing all of that, we focus on these in more and more engineering problems, and that nature gives us these possibilities to construct these perfect machines. I mean, quantum error correction for me is amazing as a concept and existence. We should also think that we get here new tools, and we should think about the utility aspect much more. Why are we doing it, and finding application cases? And I would say, if you ask me what the weakness of the whole discussion is right now in the quantum information context, it is that the real application where we think that these quantum machines are very powerful, they are very few, they're very important. But to find more of these applications, finding more algorithms that have maybe a sort of influence, impact in everyday life, this is a more and more important question to ask. It's not that you would like to build the most beautiful car, and at the end you don't know why you want to drive it. And so I would say that this is for me the bigger challenge right now, to find utility cases and more and more examples where these new machines that we are building then also have corresponding applications that open a completely new world for us.
Whoa, are you saying that what can be done now with classical systems cannot be ported to quantum computing directly?
What I'm trying to say is this, that we are now building, very close to building a fault-tolerant quantum computer.
Yeah.
I'm saying, what kind of a real-world impact problems do we actually solve that is not only of interest to physicists? Physicists get very excited. When I can solve a quantum chemistry problem, I get excited. If I do quantum sensing, I get very excited. But we also would like to find real-world applications of the sort of extra abilities that these quantum machines give us, that might change our society, our economy, in a sense of having a very broad impact. And at the moment, I would say that the real-world applications that we see where quantum computing are really a new powerful tool, much more important than classical. There are very few, and they might not always be the one, where industry, for example, would say, oh, they are the ones that will change our life, and that's the reason why we would like to buy these quantum machines. So I would say that this utility case, this utility discussion, are these things really useful in broader context, also beyond physics? This is something very important, and I think we are not discussing this enough at the moment. I mean, of course, everybody thinks about it, but I would say that I would like to see more answers and more sort of critical comments also along these lines.
Okay, I understand.
Yeah, exactly. People often say when uh, um, describing the advantages of quantum computing that we're going to be able to design drugs that will do certain things that we wouldn't be able to compute the action of these drugs with a classical computer, but a quantum computer will be able to do that. Well, maybe. We don't really have any demonstration that a quantum computer is going to allow us to design drugs that will do specific things that we want done. Or we say that the quantum computer is going to make the harvesting of solar energy more efficient. And again, maybe we don't have a demonstration that this is something that the quantum computer is going to be able to do. Now, it won't surprise me if such algorithms exist, but right now we don't really know. I think this is just what Peter is saying. We don't know. But on the other hand, it's pretty clear that problems in quantum magnetism are going to be solved by quantum computers, right?
Yeah. And maybe I add something a little bit more along these lines. So I think all of us agree that quantum simulation is solving many body problems, and in the broadest sense, quantum chemistry, high energy physics, whatever, quantum computers will be useful. I mean, there's no doubt about it. But when we look at other cases, I would say, take as example the seminal Shor algorithm. Shor had this, amazing insight, factoring numbers on quantum computers faster, beating classical machines. This has impact, for example, in quantum cryptography. At the end, you read these recent papers about, even cracking Bitcoin, with these things. Is it still safe, and so on. We should not forget that there's this one hand very wonderful and very deep physical insight or mathematical insight in this algorithm, like the Shor algorithm. But at the same time, we can now have classical quantum secure algorithm where we can do classical cryptography, where to our present understanding, quantum machines is not able to crack these codes. So I'm saying that this is sort of starting a cycle, and then you may say, oh, why do I need a quantum machine if I can just move over to a quantum secure cryptography? And this is taking away, okay? But it's sort of always starting this cycle of discussion here. But so in quantum simulation, we are in the unique situation that quantum systems like to solve quantum systems. This is the perfect marriage. But in some of the other sort of applications, like solving an optimization problem, and solving maybe factorizing numbers and all of these kind of things. Well, a quantum computer can do it faster, but classically we have then secure ways of doing cryptography that the quantum computer cannot attack. So there's this front of sort of, is it really worthwhile to buy a machine like this if I can avoid it? So there's this discussion. It's really a little bit more complicated, and finding use cases where we really know that quantum computing will at the end provide answers that we care about and that we cannot generate classically. This is very important, and this is sort of the emphasis. That's the point I would like to make, and of course, everybody agrees with that. But we need more discussions of this type.
But just to add another point to this question about post-quantum cryptography, we now have these protocols that can encrypt without being subject to quantum attack, as far as we know. There's
That's
no
the
proof.
point. Okay, very good. Right.
As far as we know.
So this cycle starts again. This is what you're saying. I agree
Yeah.
entirely. Yeah, that's
But
right.
at the same time, there's also this thing that is often talked about: harvest the data now and break it later. So you take, I mean,
I
because
agree.
people are still using uh, uh, RSA-like encryption, and if you have a quantum computer 20 years from now, and there are secrets that need to be kept for that long, then now I don't like to actually think about why people need to keep secrets for that long.
Yeah. But of course, secrets are also aging. So in this sense, there's some natural decay there. But I
Yeah.
agree entirely with what you say. Okay. Yeah.
That was a nice lively discussion there. On a similar scale on what we're talking, back to atomic clocks. How might improvements in atomic precision reshape global infrastructure or communication systems?
Well, one of the things that historically we see with atomic clocks is that every time that there's an improvement that's been made, that somebody finds a use for it. Now, the first use is almost always going to be scientific. So right now we have atomic clocks that are good to a part in 10 to the 18. Let's let's not go into the details of what that means. uh, in some sense, they're even better than that in terms of precision as opposed to accuracy. But let's not go too deeply into that. So, what are you going to use a clock that's that good for? Well, the first thing is um, uh, testing some of the most fundamental ideas in physics. For example, are the constants of nature in fact constant? Um, and these clocks give us the opportunity to test that at a level that's never been possible before. And such tests have been done and are going to continue to be done. And once we have nuclear clocks, they may even be better. And so far, we haven't seen any variation in, say, the fine structure constant from one year to the next. Uh, if we do find such a thing, or if, for example, we find that clocks of different sorts behave differently as we change their position in gravitational potential, that would be a violation of Einstein's equivalence principle. And that would be huge. So any of these things that we can do with these incredible atomic clocks are going to have big impacts on fundamental physics. Either they'll confirm what we believe about fundamental physics, or they'll seek cracks in our understanding of fundamental physics. And either way, that's incredibly interesting. But what are they going to do for say, commercial applications? Well, it may be a little bit further along the line before we have commercial applications. It may change the way in which we can process uh, 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 communicated information, because of the fact that you could have uh, uh, asynchronous information. That is, you have many different users uh, uh, sending information down the same fiber, and then you're trying to sort it out. You need atomic clocks to decide when you're going to route the information from one user as opposed to another user. And so that may allow faster communications. It may allow navigation by using gravitational maps, because of the fact that the clocks are sensitive to their positions in the gravitational potential. So one can imagine all kinds of things. What will actually happen? Well, we'll have to see.
Maybe I can add something here along these lines. I think what Bill is pointing out here is something which is very, very fundamental, and at the core of all of these developments of quantum technologies. And let me put it in the broader context. So, today we talk about quantum computers, simulators, new kind of sensors, and they're sort of offspring of our discussion of quantum science. But then, of course, we very often focus, what are the real world applications? There is, of course, having economic impact. We talk about startup companies. And if you're a young person and you want to go this line, this is the one where you become rich, at the end, or hope to become rich. But I would say that, very close to us as physicists, hard to us as physicists, is the fact that we would like to bring these new tools that we develop back into basic science. And whenever science got a new tool, think about the discovery of the lamp shift and microwave, technologies and so on. New tools always gave rise to new physics in the sense of new fundamental discovery. What Bill mentioned are beautiful examples along these lines where there are fundamental open questions. So what I get very excited about is really that these new technological developments, quantum technological developments, will feed back onto basic science, allowing fundamental new discovery. And these new discoveries, I would say that this by itself, will change physics. Maybe we discover a completely new kind of physics and new laws of nature. And I find this, from the development of mankind and impact of quantum computing and all of that, maybe one of the most exciting developments that we should not ignore. So we can either decide to go for young people the rich way, startup company, and then, maybe not, or you can try to become famous by taking these tools and bringing them into science and then discovering something new and fundamental. These are the two avenues that young people can take here. Yeah.
Whoa.
And at the same time, the um, the practical applications probably include lots of things that we can't even imagine yet. I'm pretty sure that if you had asked people like Schrodinger and Heisenberg and Dirac in 1925, what is quantum mechanics going to be good for? They would say things like, well, we can calculate the energy levels of atoms. We can calculate their transition rates. We might even be able to understand chemistry at a fundamental level. None of them would have predicted the development of the transistor, the thing that has changed the lives of almost everyone on Earth. And I don't believe that we right now can imagine some of the practical applications of quantum information science.
Yeah, I totally agree with that. Yeah.
I believe in that, yeah. That it will shift our outlook on physics and science, but yeah. Okay. I don't think we have time to move on to all the other questions. So before I go on to the closing question, there are some questions on the chat box. Okay. One from Nazri himself. Quantum engineering is becoming a major field worldwide. In your view, what distinguishes a quantum engineer from a traditional engineer, and what knowledge and mindset should universities cultivate today to prepare the next generation of quantum engineers? Peter?
If you want to answer that, I can say something, but
Well,
maybe
go
Bill.
ahead, please.
Okay.
No, from my perspective is that, we have, if you go in history, we had physics and there was electromagnetism, and the offspring of all of that together with solid state physics gave rise to electrical engineering. We had mechanical engineering. It's very clear that, now we will have quantum engineering, and the new generation, has to be educated, and also on the engineering side, knowing quantum mechanics. And so, understanding the deep concept of quantum mechanics, but then also bridging this thing to sort of real devices. And I think it needs a new generation in terms of education, but in terms of also in terms of the broad vision of thinking about all of that and understanding what quantum mechanics gives us new opportunities. And I think that this new generation is actually being created at the moment. Many universities have now new studies that are, quantum science, quantum technology, and so on. And I would say that eventually this thing will sort of separate off from traditional physics that will always be more fundamental and become more a kind of a combination, of still basic science, because many problems in quantum science and technologies are not solved yet. We don't know the answer. So it's not entirely quantum technology, but it will become more and more engineering aspects, and engineers have to understand, what the requirements are, what the limitations are in the quantum context, in the quantum world, and they have to be educated along these lines. And this will be what we have to do in the future. But I think it's already happening, actually.
Yeah, there's obviously a difference between the way a, um, uh, a fundamental physicist approaches the the creation of a quantum computer and the way an engineer does. We used to joke, I remember when I was a graduate student, that the ideal apparatus would be one that fell apart just as you finished writing your thesis. And that's obviously not the way that an engineer thinks. And it must not be the way that an engineer thinks. And while it's sort of a joke, um, an engineer is going to approach things very differently. An engineer is going to think about reliability, whereas the first time you make something in the lab, you just want it to work for long enough that you see that it can work. But an engineer wants to make something that's going to work forever, or at least for a very long time. And a lot of the progress that's been made recently is because people have taken an engineering approach. But I don't think we're anywhere near far along in that process that we don't need the fundamental physics approach as well. We need both things operating at the same time in order to make the kind of progress that we want. And I think it's happening and it's wonderful.
Yeah.
Okay, there's one from Gregory Hong. I'm not sure where is he from. Malaysia or Singapore or Indonesia, I'm not sure. Okay, good afternoon, professors. In your opinion, what aspect of quantum computing is currently overhyped and what important opportunity is still underappreciated?
Well, I think what's overhyped is the idea that quantum computing is going to solve all of the difficult problems of the world. It's going to make better drugs. It's going to make better energy. It's going to solve all of the world's problems. I think that very often when people talk about quantum information, they use that kind of language, and I think that it's not only wrong, it's dangerous because if you don't deliver on this, then it may be that the politicians will stop giving us money to do it, and and if we don't have that kind of sustained funding, we're never going to realize the actual uses that quantum computing can be put to. Now, which ones are underappreciated? I wish I knew.
Peter?
Well, I would say things that are very similar to what Bill said. I think what's maybe a little bit underappreciated right now is the fact that we find certain answers at the moment. For example, we are in the phase at the moment of building the first generation of fault-tolerant quantum computers. Still, it will happen in coming years. We might argue about is it 5 or is it 10 years or whatever, but very clearly what would happen. But I think what's sort of a little bit underappreciated is this, that very often these experimental groups and teams, they focus on sort of here is our setting and our platform. Let's try to get it there that it does what it wants. But all of these platforms at one point will hit the wall. I mean, with all of the existing platforms right now, from superconducting all the way to atomic and ions, whatever they are, photonic, we know exactly where the real problems are and where sort of hit the wall, finding fundamental problems or finding, that you cannot go any further. And so thinking a little bit ahead and seeing really, in this particular platform, we have here a fundamental problem where we are hitting the wall. Can we sort of circumvent it and be very early birds in discovering, what these problems are? And even then thinking ahead. And maybe this is something more for the theorists, because experimentalists are the ones that always like to perfect everything, but which exists in the lab. But I would say that thinking a little bit more ahead of what the problems that we have to solve, that this is sort of a point I would like to make here.
Okay, there's one from question by Ms. Doni Dwi Putra from Indonesia. Thank you for the very nice discussion. Energy is the concerning theme of this century, and only a handful of people talk about the energetics of quantum technology. From your perspective, what are the key theoretical and experimental milestones that quantum thermodynamics must reach before quantum heat engines can progress beyond proof of principle demonstrations? Oh, I don't know where that came from. Heat engines.
Yeah, maybe I can say something about green quantum computers, because maybe that's not entirely what the question was, but I think it goes in this direction.
Yeah,
So,
somewhere around that direction. Yeah.
in principle, quantum computing is unitaries and they are sort of entropy preserving. So, in principle, here's a computational model, that would not generate any heat. Of course, we always have, external steering and controls and so on, in the whole story. So I would say that at the moment we are in the phase of getting quantum computers work. And when you see what fault-tolerant quantum computers requires, that we're doing error corrections, that we have these cycles of reading out. Reading out is that you have one qubit. You read out the qubit with a microscopic apparatus. You're generating many photons. You got a photodetector. You got a computer that interprets this data. There's a lot of inefficiency here. And I think that at the end, you would like to make these things sort of more efficient by making this cycle of, for example, of error correction, doing a measurement and then feeding back on the system for the error correction. You have to make these things much more efficient. And this is where sort of energy has to be saved. So at the moment, it takes an enormous amount of energy to just operate a single qubit. And there's so much lag room for improvement. But as I said, we're in the phase at the moment, let's get these things to work and then see once it works, how we can improve it. And so this question is important, but I would say it's maybe also a little bit further down the line of working on it.
Yep. Bill?
Now, there's also another aspect of the question that was asked that has to do with the marriage of quantum mechanics with thermodynamics, and asking questions like, does quantum mechanics change the some of the fundamental ideas that underlie thermodynamics? Can you, for example, beat some of the thermodynamic limits if you invoke quantum mechanics, which is not the usual way in which we think about thermodynamics? And there's been a lot of progress in understanding quantum thermodynamics at the level of single qubits. And I think the question, in part, was about, well, where is this going to go? And my answer to that is, I have no idea. But it's great that we're starting to look at these kinds of issues.
Okay. There was one long question on qubits and possibilities, but I think Peter already answered that. That would be the most part of the question. One last question. If you were advising the next generation of scientists and engineers today, what mindset or skill set would be most essential to thrive in the emerging era of quantum technology integrated with AI? Bill?
Well, the answer is I have no idea. So I will fall back on the advice that I always give to young people, which is stay curious and don't believe everything that everybody tells you.
Yeah. And I would actually add to this that, coming back to the education point, I think that we have a new generation of young people, and they should be educated in what quantum mechanics, quantum physics teaches us about the abilities, because they are the ones that, thinking in these whole new terms. If you need the education to think in new terms, they are the ones who have to build on that. And education and sort of knowledge and training along these lines is the starting point for all of these things to come. And they will be the one making the beautiful new discoveries, that will put this quantum technology really, bearing fruits from all of these things that we're doing right now, making it work, but also then finding these applications. And but the precursor of all of this is education and understanding of the physics of the quantum physics. And I think that this is a main point for me.
Okay. Bill?
I don't have anything to add.
Okay, all right. Okay, I suppose that's about it. One last chance, if anybody would like to ask direct questions to either Peter or Bill, you can turn on your mic now before
Hi,
we.
can I ask a question?
Yeah, yes, Prof.
Thank you. Hello there. Riza from Malaysia here. Any comment from you about quantum mechanics? It says incomplete theory that will affect, things like quantum computing. Thank you.
Okay, so I think that the question that you are asking is this, will we, by building a quantum computer, at what point learn that quantum mechanics is wrong, okay, in the way that we think about? I would say that this is maybe the most fundamental and most interesting question that we can ask in the whole context. And I see us in the moment in a kind of a win-win situation. Either these quantum computing or information ideas, technologies sort of will work out in practice, and this is testing quantum mechanics by having superposition, entanglement, and ever increasing states, keeping it alive forever. And that's a very fundamental statement. But are there limits to all of that? And I think by building bigger machines and using them and benefiting from these quantum possibilities and advantage, well, there we have all of the impact that we talked about during our discussion here. But if we actually find out that there's new regions where you go to more microscopic and maybe quantum mechanics goes wrong, and there's a lot of ideas out there that it might go wrong at one point. Think about the interface with gravity and so on and so on, all of these discussions here, then this might be even more exciting. So it's kind of a win-win situation what we have here. Either it works and we can solve a lot of problems and be having exciting science, or even find that the science that we have been doing is wrong, and this would be then even more exciting because it gives rise to a completely new understanding of nature. So win-win situation.
Yes, I agree. I think that the possibility that that somehow quantum mechanics fails at some macroscopic scale is something that can be examined by quantum computing in ways that we haven't been able to address up until now. And so the results of that, there are predictions, for example, that there's not enough information available in the universe to entangle a few hundred qubits.
Okay, that will be the last of it. Thanks, everybody. And before we bid Bill good night and good day to Peter, please could everybody switch on your cameras for a photo session, guys? As usual, thank you. Cameras.
Okay.
Thank you very much. Shah, anytime you're on. Are we on, Shah?
Okay, done, Prof.
Okay, all right, thank you. All right, thank you guys. Thanks all for joining us. Very good night to you, Bill. Don't want to keep you up anymore. Very good day to you, Peter. Hope you both have good days. Nazri and his team will be sending you the certificate online after this, and for the rest of the participants. There should be a attendance link there is an attendance link in the chat box. With that, thank you, everybody. Thank you for joining us. Thanks, Peter. Thanks, Bill.
Thanks for inviting us.
Thank you. Thank you for entertaining us. Okay, bye.
Bye.
Okay, thanks, Bill. Thanks, Peter.
Bye.
Yeah.
So
Bye-bye.
long.